You hear people say, one day we'll go to Jupiter, like it is just a longer Mars trip. But if you really try to plan a round trip with real numbers, you hit a wall almost immediately. And that wall is distance. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with the basics. Earth orbits the Sun at about 150 million kilometers, around 93 million miles. Jupiter is more than 5 times farther from the Sun. When the geometry is favorable, the distance between Earth and Jupiter is around 4.2 astronomical units. That is roughly 630 million kilometers, about 390 million miles. When the geometry is bad, the gap pushes toward 930 million kilometers. So even before you think about slowing down, speeding up, or changing direction, a realistic round-trip path, with curves instead of straight lines, is well over 1.5 billion kilometers, close to a billion miles of travel. You might think, fine, it is far, but we just make the rocket fast enough, right? Say you manage a cruise speed of 100,000 kilometers per hour, around 62,000 miles per hour. That is already faster than any crewed spacecraft has cruised for long durations. At that speed, in a straight shot, you still talk about many months each way. And in the real mission, you never get a perfect straight shot. You have to accelerate, coast, then decelerate so you do not fly past Jupiter or miss Earth on the way back. And here's the first catch. You do not get to point at where Jupiter is in the sky and burn directly at it. Because while you're traveling, Earth keeps moving around the Sun. Jupiter keeps moving around the Sun. Your ship is also going into an orbit around the Sun. You're not driving across a flat map. You're changing from one racetrack to another. The standard way to do this efficiently is a transfer orbit, usually something like a Hohmann transfer. You fire the engines near Earth to stretch your orbit into a long ellipse, coast most of the way, and intersect Jupiter's path months or years later. That method is slow, but it saves fuel, and fuel is everything. The problem is, it only works cleanly during specific alignment windows, times when the relative positions of Earth and Jupiter mean that a single burn can drop you onto a path that hits Jupiter's orbit at the right time. Those windows do not pop up every week. They come roughly every 13 months, and that matters for both the trip out and the trip back, because you also need a good alignment when you want to leave the Jovian system and fall back toward Earth. So imagine you arrive at Jupiter. You do your orbit insertion burn, you spend your planned months or years doing science or operations, then you look at the clock and realize the next good departure window is not in a few weeks, it's years away. If you missed your ideal slot by crew health, by a system failure, or by simple schedule drift, you can't just hit return to Earth whenever you like. You're stuck. Your life support systems keep ticking, your supplies keep going down, and every extra year you're trapped there waiting for the right geometry eats into whatever safety margin you planned at launch. Now ask, even if you time everything perfectly, what does the total time away from Earth really look like? Not the marketing version, the conservative one. If you use current or near current propulsion, plus gravity assist where possible, plus safe margins on burns so you're not flying at the edge of engine performance, realistic estimates for a crewed craft to reach Jupiter are on the order of 2 to 3 years, one way. Double that for a return, and you are already at 4 to 6 years just cruising through space. That does not include time spent in Jupiter orbit or in its neighborhood for actual mission work. Compare that to what we have actually done. The longest continuous stay on the International Space Station is about 1 year. Even a Mars mission concept pushes us into new territory for life support, radiation exposure, and crew psychology. A Jupiter mission multiplies that. A 6-year round trip means your life support system is expected to run almost flawlessly, without resupply, for longer than the ISS has even existed as a permanent outpost. And every backup you add to make that safer adds mass. This is where the fuel versus payload fight starts to kill your return leg. For humans, you need air, water, food, medical supplies, spare parts, tools, computers, shielding, plus the actual structure of the ship. Every kilogram of those things is payload that your rockets have to push out of Earth's gravity, across interplanetary space, into Jupiter's gravity well, then back out again. And every kilogram of propellant you load to do that is itself more mass that has to be pushed. So you get a loop that feeds on itself. More payload means more fuel means bigger tanks and stronger structure, which are more payload, which demand even more fuel. Underneath that is the basic rocket rule that engineers live with. The relationship between how fast you want the ship to go, how efficient your engines are, and what fraction of your starting mass has to be propellant. It is not a gentle, linear relationship. It is a steep curve. If you want small changes in speed, you can get away with modest fuel loads. But once you stack up all the burns needed for Earth departure, course corrections, Jupiter capture, maneuvers in the Jovian system, Jupiter escape, and Earth return, the curve ramps up hard. The mass you need to devote to propellant grows faster than your ambition, and by the time you ask for enough speed to go there and come back, the numbers say your ship is mostly tank. So naturally, the next idea is, why not just go much faster and cut the time? If you could drive the trip time down from a few years to, say, 6 months one way, a lot of things improve. Life support runs for less time, radiation dose is lower, you have fewer years for things to break. On paper, this looks like the fix. Less time, fewer problems. But the speeds you need are brutal. You are now talking about cruise speeds on the order of 40 to 50 kilometers per second relative to the sun. That's about 90,000 to 110,000 miles per hour. This is 4 to 5 times faster than the fastest human re-entries we've ever done. And we only did those for minutes, not months. To reach those speeds with any kind of chemically propelled, human-rated vehicle, you need enormous burns, either extremely powerful engines or very long engine firings, which again demands more propellant, bigger tanks, stronger supports, and then you have to slow down by roughly the same amount near Jupiter or you just swing past and never stop. So all that high speed you invested in comes with an equal and opposite cost on the braking side. The energy you carry into the system is not free. You have to remove it again without cooking the crew or tearing the ship apart. And going that fast changes the environment around you from annoying to dangerous. Interplanetary space has dust grains and small rocks everywhere. At normal mission speeds, they are already dangerous. At tens of kilometers per second, a grain of dust hits with the energy of a high-caliber bullet. A small pebble hits like a bomb. You can add shielding, but again, shielding is mass, and mass pulls you back into that same rocket trap. More protection means more weight means more propellant means less room for the fuel you need for the return journey. So you're stuck in a harsh trade. If you take it slow enough that the ship, the engines, and the structure stay in known, tested regimes, the mission time stretches into a big fraction of a human working life, and your life support, your supplies, and your crew health are pushed past any experience we have. If you push the speed high enough to make the calendar look reasonable, your propellant needs explode, your structural loads surge, and the impact and heating hazards go beyond anything we've ever built for. In both cases, the part of the plan that suffers first is the fuel and margin you set aside to bring everyone back home. That's why, before you even talk about Jupiter's gravity, radiation, or atmosphere, the distance problem alone, combined with orbital mechanics and the hard limits of our rockets, already turns a trip to Jupiter and back into a simple adventure slogan, into something that, with current technology and realistic risk, is effectively a one-way mission. So after you somehow survive the trip out, you are now parked near Jupiter. And here is the part almost nobody thinks through. Getting down is one thing, getting back up out of Jupiter's grip is a completely different problem. Start with the basic force that is holding you there, gravity. At the level we call the cloud tops, roughly where the pressure is like Earth's sea level, about 1 bar, Jupiter pulls at about 24.8 meters per second squared. Earth pulls at about 9.8. That means standing on Jupiter's 1 bar level would feel about 2.5 times heavier than standing on Earth, around 2.5 g. If you weigh 80 kilograms, your body would feel like it is carrying about 200 kilograms. Your heart works harder, your muscles work harder, and any landing or ascent vehicle has to lift that much extra effective weight every single second. Now think about a rocket trying to leave that environment. On Earth, we already have to fight 1g straight up while also gaining sideways speed to get into orbit. We know how tight the margin is. On Jupiter, your engines need more than double the thrust just to hover at the same altitude. If your thrust is only a little higher than your weight, you crawl upward, burning fuel for longer, which means you use more propellant just to clear the same vertical distance. So you are in a constant fight between gravity pulling you down and your tanks draining fast. You might say, okay, gravity is stronger, just build a stronger rocket. But the real killer is not just how hard it pulls locally, it is how fast you need to be moving to actually escape its pull. This is where escape velocity comes in. For Earth, once you are high enough that the air is thin, you need about 11.2 kilometers per second of speed to escape for good, around 25,000 miles per hour. That is already extreme. For Jupiter, at the cloud tops, the escape speed is around 60 kilometers per second, roughly 134,000 miles per hour. That number is not just a bit more, it is more than 5 times faster. And energy does not scale linearly with speed. It scales with speed multiplied by itself. So if you multiply the speed by 5, the required energy per kilogram goes up by more than a factor of 25. In other words, 1 kilogram of fuel or 1 kilogram of rocket structure has to deliver over 25 times as much energy to escape from Jupiter as it does from Earth. Just changing the planet multiplies the price of every maneuver you do. So now picture the same style of ascent stack we used for Apollo. Huge rocket, 3 stages, all just to push a small capsule and lander away from Earth and toward the moon. The best chemical engines we have, like the ones on that Saturn V, have an efficiency that tops out at what engineers call 450 seconds of specific impulse. That's basically a measure of how well the engine turns fuel into exhaust speed. And that number doesn't magically jump higher just because you're at Jupiter. With that level of performance, if you try to design a single rocket that starts deep in Jupiter's atmosphere and has enough juice to accelerate itself and its payload up to nearly 60 kilometers per second, the rocket equation hits you hard. The mass you have to devote to propellant grows so much that the vehicle becomes almost all tank and engine, with a tiny fraction left for crew, life support, structure, and safety systems. We barely managed with absurd effort to build the Saturn V and get 3 people off Earth and to the moon. Scaling that up for Jupiter's escape speed is not just harder, it rapidly becomes beyond what you can assemble, test, and launch from Earth in any reasonable way. And remember, all that propellant for the ascent, plus the structure to hold it, has to be brought from somewhere. It either has to be pushed from Earth all the way to Jupiter, or somehow manufactured in the Jovian system, which today is pure speculation. So in a practical mission design, every ton of fuel you want to burn leaving Jupiter is another ton you had to carry during the trip out, which cut into your margins for life support and for the burns you needed just to get there in the first place. On Earth, at least, you start from a solid pad. Your rocket stands on concrete and steel. You can build towers, fuel lines, flame trenches. You can assemble and test on the ground. Jupiter gives you none of that. It's mostly hydrogen and helium gas. There's no solid surface at the cloud tops. If you want a launch base there, it has to float. Probably like a huge balloon or a buoyant platform sitting in a high-gravity, high-wind environment, with winds that can reach hundreds of kilometers per hour, over 300 miles per hour. Try to imagine what launching a Saturn V-class rocket from a floating platform in a continuous storm would actually involve. Your platform has to stay level, has to stay at a constant depth in the atmosphere, has to survive turbulence and vertical currents. Then you light engines that exert enormous forces and blast hot exhaust into a dense hydrogen atmosphere. Any tilt, any structural flex, any failure in buoyancy while the rocket is lit, and the whole assembly can tip, fall, or sink. You can't just build a bigger pad, because there's nothing solid to bolt it to. And there's a deeper trap hidden under all of this. Literally, Jupiter's gravity well gets steeper the deeper you go. Every kilometer you descend into the atmosphere increases the energy you'll need to climb back out. In orbital mechanics, we talk about delta V, the total change in speed your engines must provide. And that number only goes up as you drop lower. At some depth, the delta V required to get from there to escape speed is so large that the fuel mass you would need to carry becomes absurd. From an engineering and launch point of view, there's a practical no-return point, a depth below the cloud tops where the fuel required to escape exceeds what you could ever reasonably haul from Earth with multiple launches and assembly. Cross that invisible line and your ascent vehicle is not coming back out. Not because physics says it's impossible in theory, but because the mass of propellant you would need makes the vehicle unbuildable in practice, and a human crew falling past that line is effectively on a one-way dive. So when you combine stronger gravity, a 5 times higher escape speed, engine performance that doesn't magically improve, no solid launch infrastructure, and a gravity well that punishes every extra kilometer you descend, you end up with a simple, uncomfortable conclusion. It's not just that leaving Jupiter is harder than leaving Earth, it's that by the time you've built a ship and a launch system capable of doing it with humans, you've literally created something so massive, so complex, and so fuel-hungry that it doesn't fit within the launch capacity, budgets, and safety margins of our entire current civilization. And remember, all of this sits on top of the distance problem you already saw. You have to carry that ascent system out there in the first place, much of it idle dead weight for years, degrading under radiation, before you even try to light it. If distance already pushed your return plan to the edge, Jupiter's gravity well takes that fragile plan and pushes it over. Before Jupiter rips your ship apart with gravity, it tries something quieter first. It tries to kill your crew with radiation long before anyone thinks about going home. On Earth, we already have radiation belts, the Van Allen belts. They're dangerous enough that every crewed mission is planned to thread between the worst parts. Astronauts pass through quickly. They do not sit there. Now scale that up. Jupiter's magnetic field is roughly 10 to 20 times stronger than Earth's, and it stretches much farther out into space. That stronger field traps huge numbers of charged particles, mostly electrons and ions, and whips them around the planet at high speed. The result is a set of radiation belts so intense that what you get in a single day in some orbits can be more than a nuclear worker is allowed to get in their entire career on Earth. So how do we know this is not just theory? We have sent hardware there. The Galileo spacecraft in the 1990s went into orbit around Jupiter. It had electronics that were hardened against radiation, extra shielding, special components. Even then, it suffered repeated glitches and damage. Some instruments failed early. The Juno mission today flies a very strange path on purpose. It comes in from far away, dives over a pole, passes close to Jupiter for a short time, then flies far out again on a long stretched orbit. That is not for fun. That is to dodge the strongest parts of the belts near the equator. Even with that cautious path and with a titanium vault around its electronics, Juno's systems are slowly being eaten away over the course of a few years. Now compare that to a human body. A circuit can tolerate a bit flip, a reset, even losing a sensor. Your brain cannot. Your cells cannot. High-energy particles tear through DNA, cause cancers, damage bone marrow, the central nervous system. Long before they shut down a hardened probe, they will make a human seriously sick. Look at the numbers we use for safety. Space agencies like NASA set career radiation limits for astronauts on the order of about 0.6 to 1 sievert over a lifetime. That range is already associated with a noticeable increase in lifetime cancer risk. Doses around 4 to 5 sieverts delivered in a short time are often lethal, the kind of dose where many people die within weeks. In some regions of Jupiter's radiation belts, especially near certain orbits close to the planet, an unshielded human could collect that kind of lethal dose not over years, not over months, but over hours. So your first thought is simple. Fine, we will shield the crew. Just put them behind thick walls. Radiation is blocked by mass, by material. You can use water, plastic, aluminium. Things with a lot of hydrogen atoms are especially good against many kinds of space radiation. But the word thick here is not a small tweak. To bring the radiation inside the habitat down to levels comparable to what astronauts see on the ISS, in some Jovian orbits, you're looking at many tons of shielding material for every square meter of hull. That's like surrounding your crew compartment with a layer of water or plastic several tens of centimeters thick all the way around. That instantly connects back to the earlier problem. Mass. Say you design a central storm shelter for your Jupiter ship, a small inner room with heavy shielding where the crew stays most of the time near the planet. You now have a big block of dense material right in the middle of your spacecraft. If you double the mass of that central module with shielding, the rocket that has to push it doesn't just shrug. Roughly speaking, twice the mass means you need about twice the propellant to get the same speed changes, which means larger tanks, stronger structures, more complex staging, all of which add even more mass. So you enter another vicious loop. The belts force you to add shielding. The shielding inflates the mass. The mass inflates the fuel demand. The fuel demand inflates the vehicle size. And a bigger vehicle is harder to launch, harder to control, and needs even more fuel. And somewhere in that spiral, when you try to keep a realistic return leg in the plan, the numbers simply stop working. The fuel fraction you would need to carry for all the burns, including Jupiter escape and Earth return, becomes unrealistically high. So maybe then you try a different angle. You think, what if we just move quickly through the dangerous zones, dash in, do what we need, and dash out before the dose builds up? The problem is, orbital mechanics doesn't let you pick totally arbitrary paths. Once you commit to entering orbit around Jupiter, your path is largely set by where and how hard you burn your engines. If you want to go into orbit around one of the big moons, like Europa or Ganymede, or if you want a stable orbit near the planet, there are only certain families of trajectories that work with the fuel you have. Those trajectories usually involve long elliptical orbits, where the spacecraft spends a lot of time far out, then a short time swinging through low altitude near Jupiter. To save fuel, you tend to use these stretched orbits and gravity assists off the moons. That is excellent for unmanned probes, but for a crew, every close pass is a radiation hit. If you try to change the path to minimize that, you often have to spend more fuel. And remember, fuel is the thing you are already short of if you want to come home. There is also a paradox here. To really sprint through the worst radiation belts, you need to move quickly relative to Jupiter. That means you come in fast and leave fast. But a fast arrival means a big braking burn if you want to capture into orbit, or match speeds with a moon. Otherwise, you just fly straight past and never stop. Doing those big burns costs a lot of fuel, and that fuel has to be available after a trip of several years from Earth, stored safely, not boiled off, not leaked. So your clean, quick dash idea demands high fuel margins and high performance, which are exactly what the distance and gravity problems already eroded. And even if you accept a path that keeps you further out, where the radiation is lower, Jupiter's magnetosphere is huge. It stretches millions of kilometers. It even affects its inner moons differently. Some of them are deep inside the belts, some are on the edge. To target interesting places like Io's volcanic environment or Europa's suspected ocean, you can't avoid the nasty zones entirely. Your crew will still need heavy shielding, and they will still be stuck in that mass versus fuel trade. Think about what that means in practice for a human-rated mission. Every moment near Jupiter is a trade of science, exploration, or operations against cumulative radiation dose and against how much shielding mass you can afford. Probe missions can choose to accept higher risk. They can fly through more dangerous regions. They can let their instruments degrade and eventually fail. For humans, the threshold is much stricter. You can't say, if half the crew gets cancer 10 years earlier, that's okay. That is not an acceptable design requirement. So in the end, before Jupiter kills you with crushing pressure or tears your ascent vehicle apart trying to leave, it has already stacked the deck against you, just by surrounding itself with an invisible minefield of charged particles. If you don't shield the crew heavily, they die from radiation. If you do shield them heavily, the mass of that protection pushes your fuel and delta-V budget beyond what you can realistically launch, and every clever orbital trick you try to save a bit of propellant often traps you in those belts for longer, slowly cooking your chances of ever having enough margin left to turn the ship around and head back to Earth. So now you have distance trying to strand you, gravity trying to trap you, radiation trying to slowly kill you, and then you run into a very basic problem most people skip. You keep talking about landing on Jupiter as if there's a ground, a base, a launch pad. But Jupiter doesn't give you any of that. When you look at photos, your brain wants to see clouds sitting on top of some hidden solid surface, a bigger, rougher version of Earth. In reality, Jupiter is mostly hydrogen and helium gas, mixed with some other stuff. There's probably a dense core deep inside, rock or metal or exotic fluids, but that core is buried under tens of thousands of layers of fluid. There is no place where you can say, here is the surface, step out, plant a flag, and start building. As you go down from the top of the visible clouds, the pressure just keeps increasing. The temperature just keeps increasing. There's no sharp boundary where atmosphere ends and ground begins. It is more like diving into an endlessly thick ocean of gas that slowly turns into strange, compressed forms of matter. And before you ever hit anything solid, your ship, your tanks, your habitats are already far beyond what they were designed to handle. We know this not just from theory, but from the one time we actually tried to send something in. In 1995, NASA dropped an entry probe from the Galileo mission into Jupiter's atmosphere. It came in at very high speed, used a heat shield to survive entry, then opened the parachute and started sending data during descent. It lasted about 57 minutes. In less than 1 hour, it went from the upper atmosphere down to layers where the pressure was around 22 bar. That means 22 times Earth's sea level pressure. And the temperature was about 150 degrees Celsius, roughly 300 degrees Fahrenheit. Those conditions already broke it. The probe was built to handle extreme heat, extreme pressure, and it still failed at what, in Jupiter terms, is still the shallow end. The hotter, denser layers go far beyond that. Deeper down, the pressure climbs into the hundreds, thousands, and then millions of bar. Temperatures go into the thousands of degrees, long before any human-rated structure reaches that. Seals fail. Tanks buckle, electronics cook. You do not hit ground. You hit a region where the ship physically falls apart. So if there is no solid surface you can land on, you might push the idea one step sideways and say, fine, we will not stand on anything, we will float. You imagine a big floating base, a city in the clouds, sitting at a pressure where humans and machines can operate, something like 1 to 5 bar. That sounds reasonable on paper, but now you have to keep that base at a steady altitude inside an atmosphere that is not calm. Jupiter is famous for its storms for a reason. In the zones where you would want to float, you are in the middle of a system with horizontal winds that can reach 600 kilometers per hour, around 370 miles per hour, plus vertical motions, updrafts and downdrafts. You're also inside belts and zones where different bands of gas slide past each other at different speeds. Your base does not sit quietly in one place. It's constantly being shoved, tilted, lifted, and dropped. To stay at a safe pressure level, your platform has to actively manage its buoyancy, or its thrust. If it's lighter than the local gas, it floats up. If it's heavier, it sinks. And the density of the atmosphere changes quickly with height. That means you need a control system constantly measuring and adjusting, venting gas, pumping gas, firing thrusters to hold altitude within a narrow band. Because if you start drifting downward, pressures and temperatures rise faster than your systems can react. Now, think about what happens if you lose control for just a few hours. Maybe a power system fails. Maybe a guidance unit glitches. Your floating base begins to sink into denser layers. As pressure goes up, the structure is stressed more. Tanks are squeezed, holes are compressed, temperature climbs, cooling systems work harder. If they can't keep up, things overheat, seals soften, electronics die faster. At some depth, a feedback loop kicks in. Your systems fail because of the environment, and the failure lets you fall even deeper into that environment. You do not get a stall and recover moment. You get a slow, unstoppable fall into zones where no human hardware survives. Even if you somehow keep the base stable, now remember you also want to launch a large ascent vehicle from it. On a rocky planet, you pour concrete, you anchor structures deep into the ground. You know the pad is not going anywhere. Here, your pad is a floating, flexible platform being shoved around by hurricane-force winds in a high-gravity environment. You would be trying to light a rocket with thrust comparable to something like a Saturn V, while the launcher itself bobs up and down and tilts under dynamic loads. Rockets are already sensitive to small angles on solid pads. You keep the tip within a tiny fraction of a degree from vertical during liftoff, or the loads twist the structure. Here, any gust that hits your platform changes its orientation while the engines are firing. Guidance has to fight both the motion of the rocket and the motion of the base, and there's no solid reference frame. The gas around you is moving, the platform is moving. The only fixed thing is the planet's gravity pulling you down at over 2G. On Earth, if you build a launch tower, you expect it to stand untouched for years, decades. On Jupiter, you can't build anything that just sits there. Every piece of infrastructure, every pipeline, every crane would have to be part of a floating, actively stabilized system. You're stacking complexity on top of complexity just to reach a starting point we get for free on a rocky planet, a flat, stable surface. Then there's the idea some people imagine. Maybe we don't build a long-term base. Maybe we just dip in quickly with a specialized vehicle, grab some data or samples, and then climb back out. The touch-and-go way we talk about for Mars missions. On Mars, that's at least conceptually possible. You can land on solid ground, drill or scoop, then launch back into a thin atmosphere with a well-defined surface and a clear horizon. On Jupiter, once you commit to an atmospheric entry, you are now inside a dense fluid medium under strong gravity. You have huge kinetic energy from your approach speed. You have drag heating on the way in, and you have to fight both gravity and drag on the way out. To convert a downward plunge into an upward climb, you need enormous thrust and a lot of fuel in a very short time, because the deeper you let yourself fall, the harder the climb becomes. In practical terms, with any realistic chemical or nuclear engine we know how to build, you can't just dip and pull up. By the time your engines could fight the drag and gravity combined, you're already too deep, in conditions your vehicle was never meant to survive. So there is no clean profile where you bring humans down to a surface, step out, and then blast off later. There's no scenario where you hover comfortably for a while, then simply leave when you choose. You either stay safely outside the atmosphere in orbit and never go down, or you treat entry as a one-way disposal, the way we did with Galileo's probe at the end of its mission. For hardware, that's acceptable. For a crew that expects to come home, it's not. Put all of this together and you get a simple, harsh picture. Jupiter does not give you land to stand on. It does not give you a fixed launch pad. It does not give you a gentle, controllable environment to build in. It gives you a deep, moving, high-energy fluid envelope that will pull any human-scale structure down and tear it apart if you lose control for even a short time. And because there's no real ground to return to, any plan that involves going into that atmosphere with the idea of leaving again starts out already on the edge of impossible. And remember, this no-surface problem is not separate from distance, gravity, and radiation. It stacks on top of them. So by the time you're talking about floating bases and storm launches, you're already dealing with a crew that spent years in deep space, in a ship pushed to its limits, with fuel reserves that have to be carefully guarded for the escape and the journey home. The margin for mistakes shrinks close to zero, and the moment you dip below the wrong altitude, it disappears completely. Even if you say, fine, there is no solid ground and no launch pad, maybe we just dip into the upper atmosphere, get close, then leave, Jupiter's interior physics turns that idea into something closer to a suicide dive than a mission you can return from. Start with pressure. At Earth's sea level, you live at 1 bar. Your body, your buildings, your planes, everything you use is designed around that. Even military submarines, some of the toughest pressure vessels we build, start getting seriously stressed when they deal with a few hundred bar. In Jupiter's atmosphere, as you go down, models predict pressures that climb into the thousands, then hundreds of thousands, then millions of bar. That is not just more of the same. That is enough pressure to crush most materials into failure, and even squeeze hydrogen, the lightest gas we know, into completely different states. So if you think we will just engineer our way around that, ask what kind of vessel you would actually need. You would be talking about pressure holes far beyond any human-rated structure we have, much thicker than submarine hulls, using materials that can hold shape under stresses we mostly study in theory and in tiny lab samples, not in 100-ton vehicles. We do not certify habitats for thousands of bar, let alone millions, because there is no environment on or near Earth that demands that. Jupiter does. Then add temperature on top. Pressure and temperature are linked. As you go deeper, the gas gets squeezed and heated. That Galileo probe I mentioned before, it was already seeing about 150 degrees Celsius, around 300 degrees Fahrenheit, at only a few hundred kilometers below the clouds. That was enough to push it past its design limits. Deeper down, models say the temperature goes up into the thousands of degrees Celsius, hot enough to soften steel, destroy most polymers, and cook electronics no matter how well you try to cool them. So, a crewed craft cannot just punch down until it feels close enough and then hover there. It has to stay in a very thin outer shell of the atmosphere, high enough that temperatures and pressures are survivable, low enough that you are not just in empty space. That means you are constantly balancing between near vacuum on top and unbearable heat and pressure below. Any loss of control that lets you sink even a few tens of kilometers too far, and you cross from the zone your materials can handle into one where metals creep, welds deform, seals crack, and suddenly you're leaking, overheating, or both. Now, what is actually waiting for you if you keep going even deeper? At pressures of around 1,000,000 bar, what we call a megabar, hydrogen stops behaving like a normal gas. It starts acting like a metal. It conducts electricity. This metallic hydrogen layer is one of the reasons Jupiter's magnetic field is so strong. You are not dealing with air or water down there. You are dealing with forms of matter we can barely reproduce in tiny samples inside diamond anvil presses on Earth, and only for tiny fractions of a second. Ask yourself, are you really going to send a multi-ton human habitat into a region where the basic behavior of the main element, hydrogen, is not something we have tested on that scale? We can barely keep experimental equipment alive at these pressures in a lab. We do not know how a whole vehicle would respond to long-term exposure. What happens to insulation, to structural joints, to trapped gases in pores and cracks? It's not just harsh, it's fundamentally unknown territory. So you face a hard choice about how to design the ship. If you want to resist pressure by being strong, you make the walls thick, you add ribs, you use more metal. That adds mass, lots of it. If you want to avoid pressure instead, you stay high and float. But then you need big gas bags or lift structures which also add mass. In both cases, your mass goes up, and the heavier the vehicle, the more lift you need to stay afloat or the more thrust you need to climb back out. That loops right back into your delta V budget, the total speed change your engines can give you. A heavy, strongly built pressure capsule demands bigger engines and more fuel to leave Jupiter's gravity, but the fuel has to be carried from somewhere, probably from Earth. So every ton of extra hull thickness or buoyancy structure you use to survive pressure is a ton you then have to haul all the way out of Jupiter's well during ascent. The deeper you want to safely go, the thicker and heavier the ship gets, and the less realistic your escape plan becomes. And we haven't even talked about the gravitational side of deeper, because it's not just pressure and temperature that climb. The deeper you are in Jupiter's gravity field, the more energy you have to pay to climb back out. Think of every kilometer of extra depth as another bill added to your Delta V account. On Earth, if a submarine fails, you can at least mount a rescue from the surface, send another ship, drop a robot, try to winch people up. On Jupiter, if your vehicle sinks below the narrow band of safe pressure and temperature, there is no rescue. Any other ship, any other system you might send would have to descend through the same lethal layers, then somehow grab and lift a massive failing structure against strong gravity in a hot, high-pressure, hydrogen-rich medium, and then climb back out, with all the fuel penalties that implies. No amount of propellant you realistically launch from Earth is enough to give you that kind of capability. So once you're too deep, rescue mission stops being a phrase with any real meaning. This is the harsh part. For an Earth ocean, depth is a problem but not an absolute barrier. For Jupiter, depth is a one-way path. Every kilometer down adds pressure, heat, and gravitational cost faster than our engineering can compensate for. Your safety zone is a thin layer high in the atmosphere, and once your ship drops below that, the combination of structural stress and escape energy required grows beyond what your mission was ever built for. So even if you're willing to accept there is no ground, even if you're okay with floating bases, even if you say we will never go too deep, the physics of pressure, temperature, and gravity together mean this: a human mission that seriously enters Jupiter's atmosphere is not hard but doable to return from. It's something that, once started, you almost certainly don't bring back. Not because we don't want to, but because the environment eats both your hardware and your escape budget at the same time. Even just getting into Jupiter's atmosphere in one piece is a serious problem. Getting back out again with humans alive in a ship that still works, that's basically fantasy with what we have now. So what actually happens the moment your ship arrives in Jupiter's neighborhood? After years in deep space, you're falling toward a planet with huge gravity. Your speed relative to Jupiter is not gentle. You are talking about tens of kilometers per second. If your arrival speed is, say, 40 to 50 kilometers per second, that's around 90,000 to 110,000 miles per hour. Every kilogram of your ship carries a massive amount of kinetic energy, and the only way to slow down without burning absurd amounts of fuel is to slam into the atmosphere and let drag do the work. On Earth, a returning capsule like Apollo hit the air at 11 kilometers per second, and even that created extreme heating. Now, multiply that speed by about 4. The energy per kilogram does not just go up 4 times, it goes up by roughly 16 times because energy rises with speed multiplied by itself. All that energy has to go somewhere. It turns into heat in the shock layer in front of the vehicle and in the heat shield. So your heat shield for Jupiter is not just a bit tougher than Apollo, it has to absorb and shed many times more energy over a shorter distance in an atmosphere whose exact properties under those conditions we have never tested with humans. But surviving the first few minutes of that fireball is only one part of the problem. How thick, how heavy does a heat shield have to be before it can take that punishment? For Earth and Mars, we already drive ablative materials close to their limits. The shield slowly burns away, carrying heat with it. Even there, engineers worry about margins, about tiny defects, about cracks. Now push that into a regime where the heating is far beyond our tested cases. If you simply scale up thickness to stay safe, the mass of that shield grows fast. And remember what every extra kilogram means. Every kilogram in the heat shield is a kilogram you must later lift back out of Jupiter's gravity well if you intend to return. If you say, we'll drop the shield before ascent, that helps a bit, but you still had to carry it all the way from Earth. You still had to steer with it attached, and it still made your arrival and early maneuvers heavier and less flexible. You are paying a huge mass penalty up front just to not be destroyed before the real mission starts. Even if you get through peak heating without total failure, you are still flying at ridiculous speeds inside a thick hydrogen and helium atmosphere. In Earth, we talk about supersonic and hypersonic flight, Mach numbers like 3, maybe 5, maybe up to 25 on re-entry. Around Jupiter, because of the different sound speed in that gas, you could be at Mach 10 or higher for longer.
That means the flow around your vehicle is dominated by strong shock waves, hot plasma, wildly changing air properties. Small changes in angle can create big changes in force. So, what happens if your attitude control is even slightly off, if your angle of attack is wrong by a few degrees? The airflow can separate, the shock can move, heating can concentrate on one part of the hull. You start to roll or tumble instead of flying in a stable, controlled attitude. Once you tumble in that environment, you expose parts of the vehicle that were not designed to take full heating. You load structural joints in directions they were not meant to carry, and you spin the crew around, which adds G-loads on their bodies while the ship is already under stress.
Now, suppose you do manage to ride that hypersonic entry down to more reasonable speeds. What next? You still need to slow from many kilometers per second to almost zero relative speed at some target pressure level. You might think of parachutes, but chutes designed for Earth's nitrogen and oxygen atmosphere do not behave the same way in hydrogen and helium. The density profile is different. The gas is lighter. Supersonic parachutes are already hard to test for Mars. Testing them for Jupiter's conditions is even worse. You would be guessing more than you are used to for a human mission. So maybe you switch to retro rockets. You fire engines pointing down to bleed off the last bit of velocity and then hover or float. But now you are in a dense, moving medium with crosswinds that can be hundreds of kilometers per hour. Your exhaust plumes interact with the surrounding gas. They push it around, it pushes back. The vehicle can start to pitch and yaw. Small disturbances can turn into big swings. The difference between sitting at a roughly stable altitude and sliding into an uncontrolled sink is small. You do not have a wide safety band. And all of this is happening inside a storm system, not over a calm ocean. You're not descending through still air. You're dropping into jet streams, vortices, vertical flows. So you need constant, high-precision control just to keep the ship pointed the right way while drag, thrust, and winds fight over it. Remember, the crew by now has already done years in deep space. The hardware has aged. Sensors have taken radiation hits. Actuators have wear. You're asking the entire control stack to be perfect on the first and only try. Then, if your mission ever intends to return, you do not just get to say, "We made it in, we're done." You must reverse every single one of those steps on the way out. At the end of your stay, you have a heavily fueled ascent vehicle, which is itself heavy, sitting on or attached to some kind of floating base inside the same chaotic weather. You light its engines. Now your craft has to fight gravity, thick air, and winds while it accelerates back through subsonic, supersonic, and hypersonic regimes. During ascent, heating is back. Not as bad as entry in some profiles, but still serious. Aerodynamic forces shift as you climb and the air thins. Any structural weakness that developed during years of radiation exposure, corrosion from trace chemicals in the atmosphere, or mechanical fatigue now gets tested at full load. If a tank wall is a little thinner than planned, if a weld has a microscopic crack, this is where it blows. And unlike low Earth orbit operations, there is no escape tower, no abort mode that drops you into a rescue capsule. Failure means you fall back into the deep atmosphere with no way to stop. And after you finally clear the worst of the atmosphere, you're not done. You still need a burn that gets you close to Jupiter's escape speed, near 60 kilometers per second relative to the planet, or you're stuck in its gravity well. That means your ascent vehicle has to carry engines and propellant sized not just for atmospheric climb, but for huge orbital maneuvers afterwards. All that hardware rode down with you, sat in storms with you, and now has to deliver near-perfect performance on demand. Put it all together and you see the pattern. Entry is extreme heating and violent aerodynamics at the start. Descent is precision control in a dangerous fluid under strong gravity. Ascent is the same process in reverse, with a heavier ship, older hardware, and a crew that has spent years in space. Any one failure in that whole chain is mission ending, and there is no second attempt. Once you commit to that atmosphere with humans on board, you have basically bet their lives on a long list of systems working flawlessly under conditions we have never tested at human scale. Even if physics lets you draw a Jupiter mission on paper, biology cuts it down fast because now you're not just moving metal through space, you're keeping human bodies and minds alive and stable for close to a decade with almost no help from Earth. Start with the calendar, not the rocket. A realistic crewed Jupiter mission is not a 1 or 2 year stunt. Add up the pieces. You have an outbound cruise of maybe 2 to 3 years, then time in the Jovian system doing whatever you went there to do. Then you probably have to wait for a decent departure window, then another 2 to 3 years coming home. Very quickly, your total mission length lands in the 8 to 12 year range, even if you're optimistic. Now, compare that to what we've actually done. The longest continuous stay on the International Space Station is about 1 year, and that's with regular cargo ships bringing food, water, spare parts, new equipment, while people on the ground watch every sensor in real time. A Jupiter mission asks your life support and power systems to run almost flawlessly for something like a decade, without real resupply and without a maintenance visit from Earth. So what does that actually demand from the hardware that keeps you breathing? On the ISS today, life support is only partially closed loop. Air is recycled to a point, some water is recovered, but a lot of mass still comes up from Earth. Filters, tanks, backup oxygen, water, even clothes. For Jupiter, you can't afford that model. You need to recycle almost everything. Air, water, maybe even nutrients, with systems that have to run for 10 years without major overhaul. Think about leaks and efficiency losses. Imagine your water recovery or oxygen recycling is 99% efficient. That sounds great, but over 10 years, that missing 1% compounds. You slowly lose water or oxygen or key chemicals faster than you can tolerate. And you can't top up because there's no cargo ship dropping by. What looks like a tiny inefficiency in a 6-month mission becomes a slow, deadly drain in an 8 or 10-year one. That's why people talk about bioregenerative life support, basically small artificial ecosystems, plants, microbes, maybe algae, that recycle air and water and help with food. But those are still in the research stage on Earth, in labs and test beds. We haven't flown a fully closed-loop habitat with humans for years and proved it works. Yet your Jupiter ship needs that level of reliability, because we'll see if it works and fix it later is not an option when later is 3 years and 500 million kilometers away. Then, food. You can't ignore the simplest thing. A human needs roughly 2,000 to 3,000 kilocalories per day, depending on size and workload. Call it 2,500 as a rough number. For a crew of 4 over 10 years, that's about 4 people times 2,500 kilocalories per day times 3,650 days. You get on the order of 36 million kilocalories. Even if you optimistically assume ultra-dense stored food at around 6 kilocalories per gram, you're still looking at about 6 million grams, so roughly 6,000 kilograms, about 13,000 pounds of dry food. And that's before you add packaging, variety, redundancy, special diets for illness or high workload, plus margin in case the mission runs long. This is not a few pallets of rations. This is several tons of cargo that you must keep stable, safe from radiation, safe from spoilage, safe from mechanical damage for a decade. If you try to cut that down by growing food on board, you trade mass in food for mass in agriculture systems instead. Growing food in space means you need plant modules, soil or hydroponic equipment, lighting, fertilizers, extra water loops, plus the volume to put all of this somewhere. Plants need power for lights if they're not in direct sunlight. They release moisture, they shed biomass. The whole system needs sensors and maintenance. All of that is extra machinery that can fail and extra mass your propulsion systems have to move to Jupiter and back. Power is another wall you hit. Near Earth, sunlight at the top of the atmosphere is roughly 1,360 watts per square meter. Around Jupiter, at about 5 times the distance from the sun, that intensity drops to roughly 1/25th of that. You're down near 50 or so watts per square meter. So a panel that gives you a certain power near Earth gives you about 4% of that out at Jupiter. To keep the same power level, you would need panels 25 times larger.
So picture the power demands of a crewed ship: life support, computers, communications, propulsion systems for station keeping, maybe artificial gravity setups, plus heating because deep space is cold. Now try to feed that on sunlight that week. Your solar arrays end up the size of many football fields, fragile, heavy, and very hard to protect from micrometeoroids and Jupiter's radiation. Because of that, any serious Jupiter mission concept usually ends up with nuclear reactors as the main power source. They give you steady power independent of distance from the sun, but they are not simple. A reactor needs shielding so it doesn't fry the crew with radiation. That shielding is more mass, and the reactor produces a lot of waste heat that you must dump into space using radiators. Radiators have to be large enough and warm enough to glow away that heat as infrared radiation.
Large radiators are fragile. They add cross-section for micrometeoroid hits, and they also add thermal complexity. If a radiator panel fails, overheats, or cannot deploy correctly, your power system can run too hot. You cannot just open a window. You are in vacuum. Managing the thermal balance of reactors and electronics for a decade in deep space, far from sunlight, while passing through radiation belts, is a full engineering problem on its own. And all of that again feeds back into mass that must be pushed up and out of gravity wells. Then stack the human side on top. Psychology and medicine do not stay flat over 10 years. Long stays in space already cause muscle loss, bone loss, sleep disruption, mood changes, immune system shifts. We have some data from 6-month and 1-year missions, but almost nothing for 8 to 12-year runs, and certainly not in deep space, away from Earth's magnetic field, where cosmic rays and solar particles hit you harder. Picture living in a confined structure with the same few people for a decade. No chance to go outside except into a suit or a small gym module. No real-time communication with friends and family once you are near Jupiter, because radio signals can take 30, 40, 50 minutes one way. Arguments, stress, anxiety, depression, all of that has to be handled inside the crew, with maybe one doctor, limited medication, and no quick evacuation. That is a big psychological load to gamble on. Now consider the ordinary medical problems you see on Earth. Someone breaks an arm, gets appendicitis, develops a kidney stone, has a heart issue. On the ISS, in the worst case, you can get them back to Earth in hours. On the way to Jupiter or coming back, you are months or years from any hospital. Your only options are what your medical kit and training allow. Every random health risk a human normally faces becomes much more serious when you cannot abort the mission. All of this stacks on top of the physical mission constraints. Life support and food drive mass up. Power systems add more mass and complexity. Reactors and radiators bring new failure modes. And the psychological and medical risks make it harder to justify running with thin safety margins. The more conservatively you design to protect the crew, the heavier and more complex your ship becomes. And the heavier and more complex it becomes, the less delta V you have left for a safe return. So even if you had perfect engines and perfect navigation, biology still anchors you. A Jupiter mission is not just about beating distance and gravity. It's about keeping fragile human systems working for a decade in an environment where you cannot send help. And when you multiply that by all the other problems you've already seen, the idea of going there and then casually flying back to Earth stops looking like exploration and starts looking like a very slow, very expensive way to not come home. Your ship is not just a place to live. It's a pressure vessel, a radiation bunker, a cryogenic fuel tank, all at the same time. And when you stack those jobs together in the Jovian environment, current material science starts to fall apart. Think about what the hull actually goes through over the whole mission. During cruise between planets, the side facing away from the sun can sit at something like minus 150 degrees Celsius or colder. That is below minus 238 Fahrenheit. Metals contract, plastics get stiff and brittle, lubricants thicken. Then, if you ever attempted Jupiter entry, parts of that same vehicle see shock layer temperatures of thousands of degrees. The heat shield takes the worst of it, but the structure right behind it gets hot too. Now you have the same joints, the same welds, the same bolts cycling between deep cold and intense heat, not once or twice, but over and over for years. On Earth, if you cycle a metal structure like that, it develops fatigue. Tiny cracks form at the microscopic level. Every expansion and contraction make them grow a little. Seals that were tight start to loosen. Gaskets lose elasticity. Adhesives age and let go. Over a 10-year mission, with many thermal cycles from day to night, from powered to unpowered, from cruise to maneuver, those small changes add up. And the brutal part is, you cannot easily inspect every critical joint in deep space. You cannot just dry dock the ship and check every weld. So by the time you reach Jupiter, the question is not, is it brand new? It is, how much hidden damage has already accumulated? Now add radiation into the mix. High-energy particles don't just hit people, they slam into materials too. Polymers can embrittle as their long chains get broken. Insulation that stayed flexible in testing becomes hard and cracks. Cable jackets flake. Seals lose their sealing properties. Electronics suffer random bit flips and permanent damage. A single particle can knock a transistor into a stuck state, or slowly build up defects in a semiconductor so it drifts out of spec. Even metals are not immune. Radiation-assisted corrosion and swelling can change their properties. They might not snap in half, but their strength, toughness, and fatigue behavior shift in ways your design models didn't assume. For robots, we accept that. We harden some systems, we live with gradual degradation. For a human-rated ship that needs to still be strong enough for re-entry burns, ascent loads, and high-G maneuvers after years around Jupiter, you're asking materials to stay predictable far beyond their usual comfort zone. So you might say, okay, we'll just overbuild everything. More margin, more shielding, thicker structures. But remember, every kilogram of extra metal in a beam, every centimeter of extra thickness in a wall is mass you must throw off Earth, haul through interplanetary space, and then, if you want to bring the crew back, accelerate again to get out of Jupiter's gravity well. Structural strength is not free, it's heavy, and weight is exactly what your mission cannot afford to keep adding. Then you run into a very specific Jovian problem most people never think of. The atmosphere is mostly hydrogen and helium. Those are tiny molecules, much smaller than nitrogen and oxygen in Earth's air. They're very good at sneaking through materials. Over time, they diffuse through seals, gaskets, and even into some metals. That means if you have tanks, suits, or habitat skins exposed to that gas mix, you have to worry about slow, constant permeation. Why does that matter? Because a slow leak in space is not just an annoyance. It changes pressure balances. It shifts how your buoyancy systems work if you're trying to float. It can let flammable mixtures build up in places you don't want them. And it eats into your safety margins quietly. Many terrestrial designs rarely consider hydrogen or helium permeation over 10-year timescales because we don't park machines in hydrogen storms for a decade. On Jupiter, that's exactly the environment you're proposing to operate in. Now layer fuel storage on top of that. To even have enough delta V to escape Jupiter and return to Earth, you probably need high-performance cryogenic propellants, things like liquid hydrogen and liquid oxygen. Liquid hydrogen sits around 20 Kelvin, about minus 253 degrees Celsius, or minus 423 degrees Fahrenheit. Keeping that cold for a few days is hard. For a few months is very hard. For a decade with minimal boil-off while the tanks are being shaken by maneuvers and hit by radiation is a gigantic challenge. Every bit of hydrogen that boils off is propellant gone, and propellant gone is speed you can't get back. It's delta V you don't have. Lose enough over the mission and your carefully planned escape burn turns into, we can almost escape, but not quite, which means you're trapped in Jupiter space. You can try to vent, recondense, or use active cooling, but all those systems take power, mass, and complexity. You end up building not just a tank, but a whole refrigeration plant that has to run flawlessly for years. You could switch to storable propellants that don't need such low temperatures, but they're usually less efficient, so you need more mass of fuel for the same performance. And often they're toxic and corrosive, which adds more materials problems and safety issues for the crew. Either way, the combination of radiation, thermal cycling, and long timescales makes the idea of just keep this propellant ready for when we need to leave a lot less trivial than it sounds.
So your instinct is to protect yourself by adding redundancy, extra tanks in case some boil off too much, extra radiators in case panels fail, backup avionics, duplicate control lines, spare pumps, multiple layers of shielding and structure. That's normal engineering. If one thing can fail, have a second one ready. But in a Jupiter-class mission, redundancy has a brutal cost curve. Every backup tank is more propellant, structure, and insulation. Every additional radiator is more surface area to build, deploy, and protect. Every extra computer or power unit needs cabling, mounting, and shielding. You quickly move from a lean design to a massive, complex machine. And again, mass feeds directly into fuel. Fuel feeds directly into structure, which adds yet more mass. There is a point where your fully redundant, fully safe ship is so big and heavy that no existing or near future launcher can put it together affordably, or it can be assembled in space, but only if you accept that it cannot also carry enough propellant to both reach Jupiter and then lift itself plus the crew back out of the gravity well. And even if you could, your structural and materials uncertainties after 10 years in that environment would still be huge. The key problem is not that any single materials issue is impossible to solve in isolation. You can design against thermal fatigue. You can harden electronics. You can improve seals against hydrogen. You can build better cryo tanks. You can add backups. The problem is that Jupiter forces you to do all of those at once on the same vehicle for longer than we have ever run a crewed spacecraft under harsher conditions than we have ever certified for humans. And by the time you have added enough structure, shielding, margins, and redundancy to feel even close to comfortable sending people into that environment, the ship you have designed is so extreme, so massive, and so fuel-hungry that the part of the plan where it reliably turns around and brings those people back to Earth starts to look less like engineering and more like wishful thinking pasted onto the end of a decade of slow material failure. Your body is tuned for one planet, one gravity, one radiation environment. Earth. A Jupiter-class mission turns you into a long-running experiment on human physiology that nobody really knows the end of. Start with the simplest thing, your bones and muscles. On the International Space Station, where gravity is effectively zero, astronauts lose about 1 to 2% of their bone mass per month if they do not exercise hard. Muscle waste follows right behind. We fight that with hours of daily workouts, treadmills, resistance machines, cycling, and even then, after 6 months, they come home weaker and lighter in bone than when they left. Now stretch that out, not 6 months, but 8 to 10 years of mission time. Even if you build a ship with artificial gravity sections, maybe a rotating ring giving you some fraction of 1g, you will still have long stretches in microgravity during maneuvers, transfer, or system failures. Even with best-case countermeasures, you are pushing bone and muscle into a regime we have never tested. And you don't need a total collapse for it to be a problem. You only need the fracture risk to go up. Picture that in practice. In year 7, one crew member slips, hits a wall, and breaks a hip or a leg because their bones have thinned more than models predicted. On Earth, that's bad but treatable. At Jupiter distances, with limited surgical capability, limited pain control, and a spacecraft environment that requires everyone to be mobile and functional, a major fracture can be the start of a chain of problems you cannot stop. So you already have the skeleton and muscles under pressure. Now add radiation slowly loading the dice against every cell in the body. Deep space missions, even just to Mars, expose crews to constant cosmic rays and bursts of solar particles. Estimates show a Mars round trip already pushes astronauts close to their lifetime career dose limits, where we start to worry seriously about increased cancer risk. A Jupiter mission with 2 or 3 times the travel time and operations near a much stronger radiation environment multiplies that. Yes, you'll shield the habitat. Yes, you'll route the ship to avoid the worst zones, but you can't get the dose down to Earth's surface levels. You're living in a constant drizzle of high-energy particles for years. Acute radiation sickness might be avoided with good shielding, but long-term cancer risk, the slow buildup of DNA damage that can become cancer, goes up and up.
On paper, you can say, the risk is still within this percentage, but that's a model, not a human life. For the actual people sitting in that ship, you're essentially asking them to accept a large, unfixable increase in their odds of serious disease later, just to make the trip at all. And remember, any extra shielding you add to cut that risk runs into the mass and fuel wall you're already fighting. Then you get to the high G parts of the mission, around Jupiter itself. Inserting into orbit and then escaping later are not gentle burns. Some realistic profiles involve the ship accelerating at 2 to 3 G for extended periods. That means you feel 2 to 3 times your weight for minutes, maybe longer. Most healthy people can tolerate that for short bursts, but keep it going and it becomes a serious strain on circulation, vision, and brain function. Now, stack that on a crew's cardiovascular systems, which have been sitting in low gravity for years. Their hearts have adapted to not pushing as hard. Blood vessels have changed, body fluids have shifted. Suddenly, you're throwing them into long, heavy accelerations. Then maybe later, an ascent from deeper in the atmosphere where G-loads and turbulence mix. Some people will gray out. Some might black out. The margins between fine and brain doesn't get enough blood become thin. And you can't hit pause mid-burn without wrecking the trajectory. On top of bones, muscles, cancer risk, and high G-load, you see something more subtle. The immune system drifts. Long-duration spaceflight seems to mess with how your body defends itself. Studies from the ISS show reactivation of latent viruses, like herpes family viruses, and changes in how white blood cells behave. No one has 10-year datasets, but the trend is clear. Your immune system does not behave exactly the same in space. So imagine a crew 7 years into a Jupiter mission, in a closed environment where any bug that gets in circulates, with immune systems that aren't quite Earth normal. A mild infection that would be annoying but manageable on the ground can become a serious lingering problem. Repeated fevers, long recovery times, more stress. Maybe someone develops an autoimmune reaction, and the medical tools you have are what fits in a small cabinet. No intensive care unit, no specialist consultations, and your nearest real hospital is billions of kilometers away. And even if you say, fine, we'll accept bone loss, we'll accept higher cancer risk, we'll accept immune weirdness and heavy G periods, the story is not over when they land back on Earth. Suppose you somehow get the crew home, alive, in a battered but functioning capsule. Their bodies now have to readapt to 1G full-time, after close to a decade of partial gravity or microgravity. We already see that after 6-month ISS missions, walking is hard at first. Blood pressure control is off, people are dizzy, balance is poor, exercise capacity is reduced. After a Jupiter mission, the gap between we got them back breathing and they're meaningfully healthy widens. Chronic problems are likely. Some damage might be permanent. Joints, spine, eyesight, cardiovascular system all may carry scars from years of stress they were never evolved to handle. This is the part that often gets skipped in casual talk. You can't treat the crew like just another subsystem that will probably be okay. Their physiology is under constant assault. Bones thinning, muscles wasting if you ever slip on the exercise schedule. DNA slowly damaged, circulation stressed in every high G maneuver. Immune responses drifting, mental health under pressure from confinement and distance. Every one of those hits reduces their ability to respond to emergencies, to think clearly under stress, to recover from small injuries. The same little incident that would be a footnote on a 6-month ISS flight can tip into a mission-ending problem on a 10-year Jupiter expedition. And by the time they come home, if they do, the question is not just whether they survived, but whether the price their bodies paid was remotely acceptable. So when you tack, and then we bring the crew back on the end of a Jupiter mission plan, you're not just fighting rockets and gravity, you're betting against 10 years of slow, relentless physiological wear and damage in an environment humanity has barely dipped a toe into.
And you're doing it with no backup crew, no replacement, no easy aboard. If your bodies break down faster than you expected, there's nowhere for them to go. When your crew's out near Jupiter, do you actually still have Earth? Or is it just a faint light in the sky that answers long after the crisis is over? Because at that distance, even the speed of light starts working against you, and that quietly kills a lot of the safety net we rely on for human spaceflight. So what does that delay really mean in numbers? By the time you're at roughly 5 astronomical units from the Sun, around Jupiter's orbit, the one-way light travel time between you and Earth is on the order of 35 to 45 minutes depending on where the planets are. So a message you send now might reach mission control 3/4 of an hour later. They think about it, run sims, craft a reply, and that answer then takes another 35 to 45 minutes back. A simple, "we have a problem, what do we do?" loop can easily stretch past an hour and a half. That destroys the idea of real-time support. On the ISS, on Apollo, even on deep space probes like Orion test flights, controllers on the ground watch telemetry second by second. If a valve misbehaves, if a sensor glitches, they see it and respond almost instantly. At Jupiter, by the time Earth even knows you're in trouble, the situation has either stabilized on its own or spun into something much worse. Any emergency that develops faster than a couple of hours is, by definition, something the crew has to solve entirely on their own, with whatever tools, procedures, and training they brought. So, if mission control cannot hold your hand, who actually flies the ship? Out near Jupiter? The answer is the ship itself, with you supervising it. Jupiter is not a single gravity source in an empty void. It is surrounded by dozens of moons, from big ones like Io, Europa, Ganymede, and Callisto, down to small irregular bodies, plus faint rings, plus that huge magnetosphere. Your trajectory is constantly being nudged by all of that. How do you navigate that without constant help? You need highly autonomous navigation and guidance software that can take measurements, update your orbit, predict close approaches, and fire thrusters to correct, mostly on its own. Which means your life depends on code that has to run for years, under radiation, without the benefit of quick debugging from Earth. A small software bug that would be caught in days in low Earth orbit might sit there silently, only showing up as a tiny navigation bias, a millimeter per second wrong here, a millimeter per second wrong there. And what happens if that tiny error stays hidden because nobody on board notices and Earth only gets intermittent data? This is where another quiet killer shows up: compounding navigation error. A velocity error of just 1 millimeter per second, that is 0.001 meters per second, sounds like nothing, but over one day, that adds up to about 86 kilometers of position error. Over a year, more than 30,000 kilometers. If you are not constantly measuring and correcting, tiny mistakes grow into big misses. So you might say, fine, we will just track the ship very precisely from Earth. But even that has limits. Earth uses a network of big radio antennas called the Deep Space Network to talk to far probes. That system is already heavily loaded with Mars missions, solar observatories, asteroid probes, outer planet missions, and more, all fighting for time. Now at a high-bandwidth, human-rated Jupiter mission that needs constant tracking, health data, and telemetry for a decade. There will be times when you simply do not have full coverage. Antennas are busy, Earth rotates, maintenance periods happen, new missions launch. Blind periods or low bandwidth windows of days, weeks, maybe longer might not just be possible, they could be part of the planned schedule. And every hour you are flying mostly on your own, the odds go up that a small issue in propulsion, attitude control, or navigation slips through unnoticed, then quietly grows into something that costs real delta V to fix. And delta V, that total speed change you have available, is not infinite. You have carefully budgeted it. Every small correction burn you did on the way out, every course tweak near the moons, every station-keeping maneuver near Jupiter ate into it. The more you spend fixing navigation drift, the less you have left to do the big burns, the ones that insert you into the right orbit, escape Jupiter, and finally slow you down near Earth. If navigation errors grow faster than you can afford to correct them, the first thing you sacrifice is margin, then options, then eventually the return leg itself. So if you cannot depend on constant guidance from Earth, and you cannot afford big mistakes, could you at least count on a backup plan, some sort of rescue? History makes that sound attractive. When Apollo 13 had its explosion, Earth was only a few light seconds away in communication terms. Controllers saw data in real time, worked the problem, and the spacecraft itself was only a few days from home on a free return path around the moon. Now, move that template out to Jupiter. If something compromises your return trajectory there, if a main engine fails, if you do not have enough delta V left for escape, there's no quick swing around and come home option. The energy you need to climb out of Jupiter's gravity and then brake near Earth is enormous, and any rescue ship would have to climb that same energy hill, first outward to reach you, then back inward with you on board. How long would that take? Even with aggressive propulsion, any rescue mission would be on the scale of years, not days, and it would need its own life support, its own fuel reserves, its own extremely complex navigation plan. By the time such a mission could even arrive, whatever problem you had at the start would almost certainly have already played out. In simple terms, there is no practical rescue. There is only whether your original ship, with its original systems and margins, can finish the script without major deviations. That's the core shift Jupiter forces on you. When your crew is that far away, Earth is no longer the safety net it is in every mission we have flown so far. It's more like a slow, noisy back channel, good for long-term planning and analysis, useless in a crisis that unfolds over minutes or hours. You are flying a multi-year, high-risk mission in a crowded gravity field with a narrow delta V budget, and almost all of the decisions that matter for survival have to be made on board, with no second attempt. And when you remember that all of this rides on top of distance, gravity, radiation, materials, and human health already being at their limits, you see what that really means. The navigation and communication environment around Jupiter doesn't just make things a bit harder, it removes the last layer of backup humans are used to having in space. Once you commit to going that far, the mission has to work almost perfectly the first time, or there is no path home to correct it. You might picture deep space as empty and calm, but around Jupiter it's not. It's more like sitting in a shooting gallery for years at a time, while you hope the bullets stay small and miss the important parts. Start with something easy to overlook: Jupiter's rings. They're faint, nothing like Saturn's bright bands, so they're easy to ignore in pictures, but they're real, and they're made of dust, tiny particles knocked off the small inner moons by impacts. That dust orbits Jupiter along with you, and your ship is moving through it at relative speeds of tens of kilometers per second, tens of thousands of miles per hour. At those speeds, a grain of dust is not soft. It hits with serious energy. The density of that dust is low, you're not flying through a sandstorm, but your mission lasts years, not days. Every orbit, every pass, you integrate more risk. The chance of a serious hit doesn't reset, it accumulates. Even if the probability per hour is small, over a decade of operations near Jupiter, through ring planes and debris fields, the question slowly shifts from "will we ever be hit" to "what gets hit and when?" And it's not just the rings. The whole outer solar system has junk in it. Dust, small rocks, fragments from comets and collisions, and Jupiter's gravity makes things worse. Any particle falling toward that giant planet gets accelerated. So when you meet it, your relative velocity can be higher than similar encounters near Earth. Take something only a millimeter across. Hit it at 20 kilometers per second, about 45,000 miles per hour, and the energy it delivers per kilogram of its own mass is in the range of high explosives.
That means a tiny fragment, something you could barely see with the naked eye, can punch through thin metal, crack solar cells, shred antenna dishes, or gouge into thermal blankets. Shielding can soak up some of those hits, but like everything else, it has limits. You can design for a certain expected micrometeoroid flux, a certain number of impacts per square meter per year, but if you crank exposure time up to 10 years and put the ship in a higher flux environment near Jupiter, you are stressing that design envelope hard. So you look at impact protection, and you go to what we already use on some probes and on the International Space Station: Whipple shields. Instead of one thick wall, you put a thin outer bumper plate, then a gap, then the main wall. When a small high-speed particle hits the first plate, it shatters and spreads into a cloud. That cloud then hits the main wall and distributes its energy over a wider area, lowering the chance of a full penetration. It works well up to a point, but adding effective Whipple shielding over a big area is heavy. You need multiple layers, sometimes with special materials, supported at the right distances. If you decide that your long-duration Jovian ship needs robust shielding on all sides to handle a decade of elevated micrometeoroid flux, you're again adding tons of material. The mass of that protective shell does not just appear, it has to be launched, carried, and if you want to come home, accelerated out of Jupiter's gravity later. And here's that familiar loop. As you make the ship safer against small impacts, its mass goes up. As mass goes up, your fuel requirement goes up. As fuel goes up, your structure has to be stronger to hold it, which adds more mass. By the time you have a hull that feels comfortable sitting in that shooting environment for years, the numbers for your return delta V, the speed change you have available for escape and Earth return, have shrunk again. Now think about what happens when you start moving around the Jovian system. Jupiter is not alone. It has the big four Galilean moons: Io, Europa, Ganymede, Callisto, and a lot of smaller ones. Each of these bodies has its own local particle environment: dust generated by impacts, by volcanic activity, by surface processes feeding tiny grains into space. If your mission plan is ambitious, you are not just parking near one moon. You're doing multiple flybys, changing orbits, skimming near different bodies to do science. Every time you do that, you drive your ship through another hazard zone. Maybe a dust torus around Io, maybe regions where ejecta from small moons feeds into ring material. Each added flyby is another chance for a micro-impact to hit something critical. You are increasing the number of rolls of the dice you take. A probe can accept that. If it loses an instrument, the mission is still a success. For a human ship, a single unlucky hit in the wrong place can mean you no longer have a working main engine, or a healthy radiator field, or intact navigation sensors. Then you have to ask, if something does get hit, who fixes it? In low Earth orbit, if a micrometeoroid punches a hole in a solar panel or a thermal blanket, you can send up a new mission. You can retire the satellite. You can even bring it back in some cases. The risk sits in a network that can absorb it. At Jupiter, there is no backup spacecraft coming to replace you. You are the repair crew, with whatever tools and spare parts are already on board. For small things, maybe that's manageable. A damaged sensor head, a cable, a punctured external radiator line. You can spacewalk, patch, reroute, or shut down non-critical systems. But some kinds of damage are not field repairable. A cryogenic hydrogen tank with a hole in it cannot be patched easily in flight, under pressure, in a radiation environment. A main engine bell cracked by an impact cannot be swapped out in a garage. A big hit to a structural spine you're using to hold rotating sections or heavy fuel tanks is not something you fix with tape and clamps. Now connect that reality back to the mission timeline. The most likely time for you to be hit by something, statistically, is not in the first week. It's after years of sitting in that environment, when your arrival burns are already done, when your propellant is already partly spent, when your options are already narrowed. If a hit damages a critical propellant line after you've used most of your fuel to capture into Jupiter orbit, you don't have the capacity to just refuel or fire a different engine and head home early. So the combination is bad in a very specific way. The environment throws tiny, random, high-energy bullets at your ship for a decade. You can shield against some, but not all. Each maneuver near rings or moons adds new exposure. And the further into the mission you go, the less margin you have left to respond to any big failure. You're always trading fuel, time, and risk, and micro impacts quietly erode all three. That's why when you design human missions near Jupiter, you can't treat micrometeoroids and dust as small background noise. They're another factor that forces you to choose between heavier shielding and more fuel, between ambitious paths that sample many moons and safer, simpler orbits that do less. And every time you move the slider toward more science, more operations, you also move it toward higher chance that something irreparable gets hit before the return leg even starts. Add that on top of everything else you already have: distance, gravity, radiation, life support, materials, human health, navigation lag, and this shooting gallery effect becomes one more way the universe quietly shifts your mission from "we go there and then come back" to "we can probably get there, but bringing everyone home in one piece is asking a lot more than our hardware and our luck can reliably deliver." You can talk all day about clever trajectories and smart shielding, but at some point you hit the hard bottom line. Energy. The real cost to take a human ship from Earth to Jupiter, move it around, and then bring it back looks less like a bigger Mars rocket and more like a small starship in terms of total power and propulsion. Start with what we actually know how to fly: chemical rockets. You burn fuel, throw hot exhaust out the back, and get thrust. The best chemical engines we have, like high-performance hydrogen-oxygen engines, give you a specific impulse of roughly 450 seconds in a vacuum. You can think of that as a measure of efficiency, how much push you get per kilogram of propellant. That was enough for Apollo to go from Earth to the Moon and back. It's barely enough for Mars with very careful staging, refueling, and use of orbits. Now stack up what a Jupiter mission really needs. You have to climb out of Earth's gravity well, accelerate into interplanetary space, do course corrections on the way, slow down near Jupiter to be captured, maneuver in the Jovian system, and then do a big burn to escape Jupiter, then more course corrections, then a final burn to match speeds with Earth and get home safely. That's a long list of separate speed changes your engines must deliver. Your total delta V is huge. With chemical propulsion only, the rocket equation hits you brutally. As that total delta V requirement climbs, the fraction of your mass that must be propellant climbs faster than you think. You end up in a regime where your ship at departure is almost all fuel, with a tiny slice left for structure, life support, shielding, and payload. That might be tolerable for an uncrewed probe the size of a car. It's not workable for a human habitat, radiation bunker, and ascent vehicle wrapped into one. So maybe you say, fine, chemical rockets have hit a wall, let's go nuclear thermal. And that concept, you heat hydrogen in a reactor and throw it out the back. You can get specific impulse numbers in the 800 to 900 second range, roughly double what chemical gives you. That's a big step. It means for the same delta V, you need less propellant, or for the same propellant mass, you get more delta V. But even if you double efficiency, you're still in the same basic game. The delta V stack for Jupiter is so big that you're still carrying a huge amount of propellant relative to your dry mass. Maybe you shave off some years of travel time, maybe you shrink your tanks a bit, but you don't suddenly move into a regime where the mass ratios are friendly and you have comfortable margins. You are still flying right on the edge of what's realistic. And now you have added a new problem. You're carrying an operating nuclear reactor, or several, from launch onwards. You have to make sure it is safe on the pad, safe in Earth orbit, safe during any possible abort, safe during cruise, safe if you ever dip into an atmosphere, and if anything goes wrong, you're not just dealing with broken hardware, you're dealing with a hot reactor you cannot easily turn off or throw away. The safety constraints on launching multiple nuclear thermal stages for a human mission are not small. So what about the high-efficiency systems we already fly on some probes? Ion engines, Hall thrusters, electric propulsion. These can have specific impulse in the thousands of seconds. On paper, they look perfect. They sip propellant. They can slowly build up huge speed changes over time. But here's the catch. They are very low thrust. They push like a gentle breeze, which is fine for unmanned craft that can take months or years to spiral around a planet or adjust in orbit. For a crewed Jupiter ship, you need two things these engines are bad at. You need high thrust maneuvers to keep G-loads safe and short, and you need strong burns to get in and out of deep gravity wells without hanging around in dangerous zones for too long. An ion engine that puts out a fraction of a Newton is not going to lift a large human-rated vehicle out of Jupiter's grip in any reasonable time, and they are power-hungry. To run a cluster of them at useful levels, you need megawatts of electrical power. But out at 5 astronomical units, sunlight is about 25 times weaker than near Earth, as we said earlier. Solar panels that work great in Earth orbit deliver only about 4% of that power at Jupiter. So to feed megawatt-class ionic propulsion, you would need solar arrays of extreme size, fragile, massive structures that are almost impossible to shield and protect for 10 years. Practically, a human Jovian ship using electric propulsion will need nuclear reactors to power the thrusters. So now picture this setup. You are relying on reactors both to run the ship and to drive your electric or nuclear thermal propulsion. Reactors are not like normal engines. They generate a lot of waste heat that you have to get rid of. In space, your only way to dump heat is through radiation. You need big radiator panels spread out to glow away that energy as infrared light. If you're talking kilowatts to megawatts of power, those panels get large very fast. Large radiators are trouble for 3 reasons. First, they are mass, and mass is always your enemy in a deep space mission. Second, they are fragile. Thin structures sticking out from the main hull, sensitive to vibrations, micrometeoroids, and manufacturing defects. Third, they increase your cross-section, making you a bigger target for dust and debris. So just to keep your propulsion system and your life support from overheating, you accept more mass and more vulnerability. At this point, people often jump to the sci-fi solutions. Antimatter engines, fusion torches, beamed power sails, things you see in games and movies that make Jupiter trips sound almost easy. But right now, all of that is still fiction in engineering terms. We do not have a working fusion rocket. We do not have practical antimatter production and storage for propulsion. We do not have a beamed power network set up across the solar system. Could some form of advanced propulsion change the picture? Yes, absolutely. If you had a compact fusion drive with huge exhaust velocity and high thrust, you could cut travel times dramatically, shrink propellant mass, and give yourself enough margin to carry serious shielding and redundancy. But notice what that really implies. To make Jupiter round trips with humans feel manageable, you need a level of technology and industrial capacity that we simply do not have and will not have for quite a while. So you're stuck. Today, with real physics and real hardware, chemical rockets that hit a wall in performance, nuclear thermal concepts that help but not enough, electric engines that are efficient but too weak for the big burns, reactors that bring their own mass and heat problems, radiators that add vulnerability, and sci-fi drives that are still just ideas. Every attempt to improve the propulsion side runs into the same trade. Better performance usually demands more complexity, more mass, and more risk. And by the time you add up all the energy you must spend to leave Earth, cross the huge gulf, dive into Jupiter's deep gravity field, survive there, then climb back out and slow down near Earth again, the honest conclusion is simple. The propulsion and power budget for a truly round-trip crewed Jupiter mission is closer to building a small starship than to launching a scaled-up Mars rocket. And our current rockets, reactors, and engines are nowhere near that mark. By now you've seen radiation, gravity, distance, life support, propulsion, materials, health, navigation, all pulling against you. The real reason you don't bring humans back from Jupiter isn't one of those things by itself, it's all of them stacked and multiplied together. Think about how we normally talk about risk. You might say, okay, the chance that life support totally fails in 10 years is maybe 1% if we overbuild it. The chance that propulsion has a catastrophic issue is another 1%. Maybe navigation, materials, radiation shielding, medical all sit in that same low but not zero band. If you looked at each subsystem alone, you could convince yourself the risk is acceptable. But a Jupiter mission doesn't let those risks live alone. You're flying with all of them at once for a very long time. If you have 10 major systems, each with a 1% chance of killing the mission over a decade, you don't end up with a 1% overall risk. You end up multiplying those probabilities, and the total chance of everything going right drops fast. Jupiter missions sit in that multiplication zone, where small risks stack into a large one. For a crewed return, you don't just want maybe we make it, you want a high probability of success, something you can justify to the people getting on board. But the more you look honestly at each subsystem's long-term reliability under Jupiter conditions, the harder it becomes to keep that combined success probability in a comfortable range. Each new fix you add to one area, like more shielding or more redundancy, often adds complexity and new failure modes somewhere else. Now look at abort options. In Apollo, they baked abort-to-Earth paths into the plan. If something went wrong at certain stages, you could fire the engines a different way and swing back home. You had free return trajectories around the moon, where even if the engine never lit again, gravity would bring you back to Earth's neighborhood in a few days. Mars architectures at least imagine similar ideas, where you fly a path that can bring you back without a perfect insertion. For Jupiter, that comfort is gone. Once you commit to some of the big maneuvers, like that deep Jupiter capture burn or a trajectory that threads near multiple moons, there is simply no physically possible way to get enough delta V from your engines and remaining fuel to swing back early. An abort, if you can call it that, might mean changing your target from one moon to another, or burning into a safer orbit and riding it out. It doesn't mean redirecting onto a quick path home. So imagine telling the crew, if the main engine fails after this point, you can't go back to Earth. Your best case is to park around an icy moon and try to survive with what you have. That's not an abort mode in the sense we normally use for human missions. That's a one-way plan with different possible endings, none of which involve a fast rescue. Once you pass certain points, you're locked into a long, narrow path with no exits that lead home. Then consider how long you're asking the hardware to stay healthy. Probes we send to Jupiter now are considered successful if they last 5 to 10 years. They slowly degrade from radiation, thermal cycling, and wear, and when they finally die, everyone celebrates the data they sent and moves on. They were designed to operate until failure, and failure is actually in the plan. For humans, that's not acceptable. You need the ship not only to keep working, but to keep working with margin until after the crew is safely back on Earth. Every major subsystem have to carry enough life in it to survive the worst phases late in the mission, like re-entry at Earth or escape from Jupiter. That's a much harder standard than run until something breaks. Yet the environment is the same, or worse. More radiation, more cycles, more time. We also normally like to test things step by step. Before Apollo landed on the moon, we flew missions in Earth orbit, then around the moon, then in lunar orbit, then short landings. For Mars, you can imagine a path where you test transit systems in cislunar space, then in Mars orbit, then maybe short Syrtis surface. Each step teaches you something under gradually harsher conditions, and you catch design flaws before committing to the full mission. For Jupiter, there is no close stepping stone that truly matches its conditions. You cannot build a Jupiter practice range near Earth. You cannot send humans to something almost like Jupiter first, so your first real crewed Jupiter mission would be a direct jump from "we have never taken humans beyond the Earth-Moon system" to "we are going to run a decade-long deep space expedition into the most hostile planetary system we know." That is a huge leap, with no small rehearsal that matches the stakes. So you end up with this uncomfortable situation. Each individual technical problem, delta V, radiation, life support, materials fatigue, navigation delay, human health, looks barely solvable in theory if you throw massive effort at it. But when you combine them in one mission profile that has to work the first time, with no rescue, no real abort to Earth, and hardware expected to survive longer and under harsher conditions than any probe we have ever flown, the effective chance of getting all the way back drops into a region you would never accept for human lives. This is how hard turns into effectively impossible, not because physics puts an absolute red line through the idea of a Jupiter round trip, but because when you put all the real constraints together, the probability curve for a safe return collapses. You can, with enormous cost, design something that leaves Earth and reaches Jupiter. Probes do it now, designing something that can take humans there and then reliably get them all the way home with our current technology level, operational experience, and risk tolerance is a different problem. And that is the key. Nobody is saying you cannot sketch a miracle ship on a whiteboard that solves one or two of these issues elegantly. You can. But Jupiter does not ask for one or two fixes. It asks for all of them, working together over a decade with no second chances. So when you hear, why can't we just go to Jupiter and come back? The honest answer is because once you stack all the low probability failures and all the missing technologies together, just disappears. And what is left is a mission that on paper might reach Jupiter, but in practice almost certainly does not bring its humans safely back to Earth. We already send visitors to Jupiter. They are just not made of flesh. And the fact that they do not need a ticket home is exactly why they can go places humans cannot. So ask the straight. Why can Galileo, Juno, and soon Europa Clipper dive into that hostile system while you and I cannot? The first big reason is simple. Robots can accept risks that would be completely unacceptable for a human crew. Galileo went through fierce radiation and slowly died from it. Juno is literally flying in orbit designed to delay its own radiation death. Europa Clipper will fly through intense belts knowing its electronics will degrade. If a probe fails at Jupiter, it's a loss of hardware and data. That hurts, but nobody dies. Engineers design these missions knowing that a single point failure in the wrong place, a stuck antenna, a memory glitch, an instrument shorted by radiation, can end the whole mission. We accept single point failures because the payload is metal and silicon, not people. Now flip that to a crewed mission. You cannot say, if the main life support loop fails, we will just accept the loss. You cannot say, if a navigation computer locks up from radiation, we're okay losing the ship. For humans, every critical system needs backups, sometimes backups of backups. You control risk by stacking redundancy and margin, and that blows your mass and complexity through the roof in ways probes simply do not face. That ties right into the next difference, life support. A robot needs power, thermal control, and a way to talk to Earth. That's it. It doesn't breathe, drink, eat, sleep, or go insane from isolation. That means when you design a Jupiter probe, almost all of your mass can go into instruments and propulsion. A few tons are enough to do real science. Think about that. A 2-ton spacecraft, about the mass of a car, can carry a camera suite, a magnetometer, spectrometers, a thick radiation vault, and a propulsion system that lets it break into orbit and maneuver. The rest of the rocket stack is spent boosting that fairly small piece of hardware out of Earth's gravity and onto Jupiter. Now compare that with what a human habitat needs. You need a pressurized volume big enough to live in for 8 to 12 years. Full environmental control, near complete recycling of air and water, thick radiation shielding, storage for several tons of food or full-scale agriculture modules, exercise gear, medical equipment, spares, and all the structural support for that. Suddenly, you're not talking about 2 tons. You're talking about tens of tons just for the habitat, then more for propulsion, then more for ascent and descent systems if you plan to go near the atmosphere or the moons, then more for shielding and redundancy. You rapidly move from we can launch this to this looks like an orbital station plus a deep space drive plus a lander all bolted together. The line between we can launch this and this is fictional is basically the life support mass. And then there's the mission profile itself. Robotic missions are one way by design. They leave Earth, travel for years, do their operations, and eventually die on station or crash into the planet or a moon. Their job is to return data, not to return themselves. That changes everything about the fuel and power budget. If you don't need to bring the hardware home, you can plan your burns and your orbits to spend every last kilogram of propellant on science and maneuvers. You can accept that the spacecraft will eventually be in a path that leads to destruction. You can let it dive deeper into radiation or closer to the planet at the end, because there is no next leg you have to save fuel for. With humans, you don't have that luxury. Every maneuver you plan has to be compatible with leaving enough delta V in the tank to get out of Jupiter's gravity and break near Earth again.
Every "let's dip a bit lower" decision hits the escape budget. You can't burn down to dry tanks just to map one more moon, because if you do, there is no way home. Robots can push right up to that edge. Humans cannot. And that gap gets wider as onboard autonomy improves. The one big argument for putting humans on site was always humans can make fast decisions, adapt to the unknown, do flexible exploration that's hard to program. That's still partly true, but robotics and AI are getting better every year. Probes already navigate hazard fields, adjust imaging plans, and respond to anomalies on their own. As that capability grows, a robot at Jupiter can notice something interesting, tweak its orbit, repoint instruments, and handle unexpected conditions locally, then tell Earth what it did. That reduces the value of having a human brain physically sitting in that environment. The more our machines can think and react without direct human guidance, the less you gain by risking human lives in the same spot. Then you have to ask, what exactly do you need humans on site for? Jupiter's atmosphere, its magnetic field, the geology of its moons, the potential subsurface oceans on Europa or Ganymede, all of that can be studied by remote sensing, flybys, orbiters, and landers. We already do atmospheric composition by spectroscopy. We measure fields with magnetometers. We image surfaces at high resolution. We'll send landers and possibly ice-penetrating probes. Would a human geologist on Europa be useful? Sure. Could a human engineer on a floating Jovian platform fix things on the fly? Maybe, but the marginal scientific or operational benefit of putting a person there is not huge compared to what we can do with robots, and the cost and risk curve for humans is not linear, it's exponential. For Jupiter, the return on investment for humans is deeply negative. You multiply risk, mass, complexity, and ethical questions by huge factors just to gain a small edge in decision-making and flexibility that robotic systems are rapidly catching up to anyway. You don't need boots on that ground to do great science. The atmosphere doesn't care if the instrument package that samples it is human-operated or automated. So when you look at what we actually do, you see the pattern. We send metal and silicon first. We let them soak up the radiation, test the orbits, sample the hazards, and in the Jovian system, they're not scouts for human missions. They're the main act, because they can take the kinds of risks that would make any human round-trip plan insane. And that's the crucial difference. Robots don't need food, water, air, or a way back to Earth. They just need enough power to run and enough shielding to last through their mission. So they fit inside the narrow band of what's realistic for Jupiter. Humans blow right past that band the moment you add "and then we bring them home" to the mission statement. So here's the uncomfortable question. Is Jupiter actually impossible, or is it just impossible for a civilization like ours? Because Jupiter doesn't break physics for a human round trip. It breaks what's realistic for 21st century Earth. If you look at this only through pure physics, nothing in the laws of nature says you cannot build an absurdly capable ship. You could, in theory, design a mega-structure vehicle with fusion engines that throw exhaust out at tens or hundreds of kilometers per second, artificial gravity rings spinning to give you 1G on board, meters of water or ice around the habitat to eat radiation, huge farms inside that recycle air, water, and nutrients, a whole self-sustaining ecosystem in space. On paper, that solves a lot. Your fusion drives cut travel time and shrink fuel mass. Your thick water shield makes Jupiter's radiation manageable. Your rotating sections keep bones and muscles healthy. Your internal ecology feeds the crew for decades. In strict physics terms, none of that is forbidden. The equations do not object. The real problem is, who actually builds that? Because now you are not talking about a mission, you are talking about an industrial base on the scale of a Kardashev-style civilization, one that can throw around ridiculous amounts of energy and material almost as routine. Our reality is very different. Our rockets are expensive. Our access to orbit is still limited. Fusion power on Earth is not even deployed at scale, never mind in a compact rocket engine. Our experience with closed-loop habitats is measured in months, not generations. So even though physics is open to the idea of a Jupiter megaship, the engineering feasibility for us today is basically zero. You would have to transform our whole civilization first, then think about Jupiter later. And that leads straight into the economic wall. Imagine you somehow convince the world to aim for a single crewed Jupiter mission with a genuinely realistic chance of bringing everyone back alive. Not maybe we get lucky, but a design with thick shielding, huge redundancy, advanced propulsion, full life support tested for decades. The cost is not a few trillion. It starts to look like a serious fraction of global GDP spread over many years. That means you're not just funding a space project, you are making trade-offs against everything else humanity cares about. Climate adaptation, healthcare, energy transitions, education, basic infrastructure, security, all of it. You're saying we will freeze or slow many of these to pour that money, effort, and talent into one ultra-risky mission for a handful of people. When you look at it that way, you see why it is a non-starter. The opportunity cost is enormous. Then there's the ethical side. Knowing everything you know now, the stacked risks, the lack of real rescue, the compounding probabilities, can you honestly strap a crew into a Jupiter ship and say, "We think you'll probably come back," when probably is doing a lot of work? We already argue about acceptable risk for Moon and Mars missions, where you can still design abort paths and partial rescue options. For Jupiter, the probability curve leans much closer to this is effectively a one-way trip with a small chance of return. That might be something a few volunteers would accept. People already sign up for dangerous jobs. But at the level of agencies and societies, sending people into an environment where rescue is essentially impossible and return is deeply unlikely crosses a line. You are no longer just managing risk, you are knowingly launching people into a situation where if anything big goes wrong, there is literally nothing you can do to help them. Then look at our actual technology roadmap for the next century. When you follow the trend lines honestly, you see moon bases, Mars missions, maybe asteroid mining, more advanced stations in cislunar space, more reusable rockets, nuclear power in space. All of that is plausible. The stepping stones that would make Jupiter reasonable, like routine fusion power, cheap access to orbit for megastructures, giant space factories, closed-loop habitats proven over many decades, are nowhere near deployment. The gap from where we are today to we can test a Jupiter-class ship with people is bigger than the gap from the Wright Flyer to the ISS. And we did not jump from Kitty Hawk directly to a space station. We took thousands of smaller steps. For Jupiter, we don't even have the first few steps laid out. We are still arguing about how to do Mars, and that's a much simpler problem. So what should your viewer actually take away from all of this? When you talk about humans going to Jupiter and then returning, you're really talking about a civilization so advanced that ours would look primitive to it. A culture with energy, resources, and technology far beyond what you see on Earth today. For that kind of civilization, a Jupiter round trip might be a tough but doable project. For us, now, Jupiter is effectively a one-way destination. We can reach it with metal and silicon, with probes that accept radiation, risk, and one-way tickets. But we cannot responsibly send fragile bodies there expecting to see them walk back on Earth. The physics is not the barrier, our civilizational scale is. And that gap, the one between what the raw laws of nature allow and what a real present-day human society can actually build, pay for, and ethically sign off on, is why for every practical purpose that matters to people alive today, humans don't come back from Jupiter. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.